let's dive in. So in Java, we love using threads, right? They make our apps feel snappy and super responsive. But the moment you have more than one thread running, you open up a whole new can of worms. You run into this problem of data inconsistency. So today, we're going to explore why managing threads is such a critical skill and why it's a very delicate balancing act.
I mean, the whole reason we do multithreading is for performance. Think about it like having a bunch of workers building a house. Instead of one person doing everything, one brick at a time, you've got electricians, plumbers, and carpenters all working in parallel. And the result? The house gets built way faster. And for our apps, it means they feel incredibly responsive. But here's where it gets messy. What happens when all those workers need to use the one power drill on the site? In the world of programming, what happens when all of your threads try to read and write to the exact same variable at the exact same time? Well, you get chaos. Total, unpredictable chaos.
And this chaos actually has a name. It's the first and honestly the most common headache you're going to run into with multithreading. It's called a race condition. It's basically a mad dash for threads to access some shared data, and trust me, the results are almost never what you'd expect.
Let's make this super simple. Imagine you have a basic counter. If I ask one thread to increment it, the count goes up by 1. If I ask a second thread to do it right after, the count goes up by 2. Simple enough. But what if they try to do it at the exact same microsecond?
So here's how things can go completely wrong. See, a simple operation like count ++ isn't actually one step. It's 3. You read the value, you add 1 to it, and then you write the new value back. So thread A reads the count, it's 0. But before it can write its result, the scheduler pauses it and lets thread B run. So thread B also reads the count, and guess what? It's still 0. Then thread A wakes up and writes its result, 1. And right after, thread B writes its result, which is also 1.
And the final result? 1. Wait, what? We called the increment method twice, but our count only went up by 1. An entire operation just vanished into thin air? That is the core of a race condition. The final result depends entirely on the random, unpredictable timing of how the threads get executed.
So a race condition isn't just a regular bug. It's this sneaky, devious bug that might only show up once in a blue moon, making it an absolute nightmare to track down and fix. It's pretty much the root cause of all kinds of flaky, unreliable behavior in concurrent apps.
Now, if you thought race conditions were a bit of a mind bender, buckle up. The problems can get way, way more subtle. We're about to venture into territory where things go wrong for reasons that even seasoned developers can miss, because these problems are happening way down at the hardware level.
I love this quote because it really sets the stage. We're about to look at issues that aren't just about timing. They're about the weird, counterintuitive ways that modern computers cheat to try and get every last ounce of speed.
And this right here is our first hidden trap. To be fast, every CPU core has its own little private memory stash called a cache. It's super fast. So when a thread running on core 1 updates a variable, it might just update its own local cache, not the main memory that everybody else sees. It's great for speed, but it creates a massive disconnect. And this leads to what we call a visibility problem. So thread A updates its count variable to 1 in its own little private cache. But thread B, which is running on a different core, is still looking at its own cache where the value is still 0. As far as thread B is concerned, the update never even happened. The change is completely invisible, and now it's making decisions based on stale, totally wrong data. As if that wasn't bad enough, here's another hidden trap for you. To squeeze out even more performance, both the Java compiler and the CPU itself will literally reorder the instructions in your code. They can do this as long as it doesn't change the result for a single thread. So, for example, you write code that does 3 things in order. 1. Create a new object. 2. Fill it with data. And 3. Make a variable point to it. But for performance, the system might decide it's faster to create the object, assign the variable to it first, and then fill in the data last. For a single thread, who cares? The result is the same. But what if another thread sees that variable right after step 2? It gets a pointer to a half-built, totally uninitialized object. It's a recipe for disaster. Okay, I know. Race conditions, visibility problems, instruction reordering, it sounds pretty bleak. But don't panic. Java gives us the tools we need to bring some order back to this chaos. The trick is telling Java exactly where and when our threads might step on each other's toes. So, the #1 tool in our toolbox is the synchronized keyword. The best way to think about it is like a key to a room. When a thread wants to run a piece of synchronized code, it first has to grab the key, or the lock. And as long as it's holding that lock, no other thread can get in. This whole idea is called mutual exclusion, and it's a simple guarantee. Only one thread at a time, period.
Let's look at how this fixes our original counter problem. All we have to do is add that one word, synchronized, to our increment method. Boom, race condition solved. Now, if two threads try to call it at the same time, one of them is forced to wait until the other one is completely finished. The final count will always be correct.
Now, synchronized is a powerhouse, but it's not our only tool. Let's compare it real quick to another keyword, volatile. Synchronized is like a bouncer at a club. It only lets one thread in at a time. It fixes race conditions, and as a bonus, it also fixes those memory visibility problems. Volatile, on the other hand, is more like a public announcement system. It doesn't stop anyone from coming in, but it guarantees that if a value changes, everyone sees that change immediately. So it fixes visibility and reordering, but it does not fix race conditions. They are very different tools for very different jobs.
So we have the tools to make our code thread safe. Awesome. But, and this is a big but, this safety comes at a price. If you start using these tools without understanding the trade-offs, you can introduce a whole new class of problems, and they almost always revolve around performance. This quote is so important. The whole Java memory model is designed with one assumption, that threads work alone and should run as fast as possible. The moment we decide to share data between them, we're creating an exception to that rule, and it becomes our job, the programmer's job, to manage it very, very carefully.
So what are the costs? Well, first, just the act of grabbing and releasing a lock takes time. It costs CPU cycles. Second, if you go overboard and synchronize everything, we call that over-synchronization, you completely kill the parallelism you were trying to achieve in the first place. And third, you can create some truly gnarly new bugs, like a deadlock, where two threads grind to a halt because each one is waiting for a lock that the other one is holding.
And you know, the challenges are always evolving. In modern Java, we have these amazing lightweight virtual threads that let us handle thousands of tasks at once. But the old-school synchronized keyword can cause a huge problem called thread pinning. Basically, if a virtual thread enters a synchronized block and then has to wait for something slow, like a network request, it gets stuck. It's pinned to its system thread, blocking it completely. If this happens enough, your whole application can just grind to a halt.
And all of this brings us to the ultimate question that every single concurrent programmer has to ask themselves. It's not just about making the code safe. It's about finding that razor-thin balance between making sure it's correct without throwing away all of the performance that made us want to use multiple threads in the first place.
And that is the perfect place to wrap this one up. Our journey into concurrency is just getting started. Now that we know how to stop threads from crashing into each other, our next step is to figure out how they can actually work together. And for that, we'll need to learn how they communicate using Java's wait and notify mechanisms. I'll see you then.